In the systems programming video series, we're talking through the textbook, dive into systems. We're moving on now to section 4.6 on bitwise operators. Bitwise operators give you a little bit more direct control to manipulate the individual bits of often a byte or something like that, but whatever, some collection of bits in a more direct way. I mean, we know that we can take a collection of bits and add one to it, right? So that exists, and that can increment you through the various possible bits held in an amount of memory. But that can get very complicated if there's something other than addition that you were trying to do. So in any case, this gives you more direct, in a sense, kind of more powerful control over the individual bits of your memory. And we'll see why that would be a valuable thing, like what applications that has. So there's bitwise AND. Now keep in mind that bitwise AND is not the same thing as logical AND. So let's, since there's a table right here, let's go ahead and see bitwise AND is talking about ANDing two bits, simple bits. We often write it with the ampersand symbol. And, so 0 and 0 is 0, 0 and 1 is 0. This is, I think, probably to most viewers, a familiar sort of truth table for conjunction, or however you want to think about this. But keep in mind that this is bitwise, so we're only seeing it applied to individual bits. When we apply it to collections of bits, then because of its bitwise nature, we only perform this operation bit by bit, which is different from what you would get if you were to do the logical, right? The double ampersand, the logical conjunction is different, right? Because, for instance, what if you had the sequence of bits 0, 1 and the sequence of bits 1, 0? Now, if you bitwise AND these, you get 0, 0. But logically, again, referring to how C understands true and false, this would be true because it is not 0. The only number or sequence of bits that is interpreted by C as false is a sequence of all zeros. So since this is not all zeros, it is regarded as a true value. And this, likewise, is also regarded as true, but when we AND them bitwise, we get false. So when you double conjunction, right, or do the logical AND, this is not what you get, right? So we don't necessarily even need to worry about how the computer actually does logical AND. At least not right now. That actually might be kind of an interesting exercise later on. But for now, just know that to perform logical AND, you cannot simply perform bitwise AND. They don't always get you the same results. Not only is there an AND, there's also an OR, a NOT, right? So OR is, I think, kind of obvious. NOT is actually, in fact, exactly the same thing as a bit flip. So here's bitwise OR, nothing, I don't think, terribly interesting or new. There's the XOR operation, which, if you learned about this kind of stuff in an intro programming or a logic setting, maybe you're not familiar with XOR. It doesn't come up in those settings quite as often. So let's look at the table for bitwise XOR. It's called XOR because it's supposed to be exclusive OR. We'll write it with this caret symbol. And so if it's exclusive OR, then what we mean is that you have one but not the other, or the other way around, right? The order doesn't matter, but so either A is 0, B is 1, or A is 1, B is 0. In either of those cases, it evaluates to 1, which we regard as kind of like a true value. So those are the true values. But if it's anything else, right? If it's neither or if it's both, then we return 0. So that's the exclusive OR, right? It's supposed to be an OR, but it is supposed to be exclusive. If one of them is true, the other one is not. So that's the exclusiveness part. Anyway, there's bitwise NOT, which is somewhat obvious. It's a bit flip. Now there's another category, right? This is a non-logical operation because it doesn't correspond to, truth values in a way that you would tend to think. This is bit shifting. So you can shift to the left or the right. We'll start off talking about shifting to the left. Now here it talks about how in the absence of overflow, shifting to the left increases the value of the result. That should make sense, right? Because if all the bits are going to higher, more significant places, I guess unless you have all zeros, but as long as there's at least one 1 and it gets moved to a higher position and there's no overflow, right, which is a necessary concern, but so long as there is no overflow, then the, sort of magnitude of this thing is increased. So here, if we take this number and regard it as an unsigned integer, then this bit is going to get truncated, right? We're going to left shift everything. That bit is going to get truncated, which in a way is an overflow. And so this quantity is actually going to become smaller. And if you work out the exact values before and after the shift, you find these two values, so you really explicitly see it getting smaller in that way. And I guess, I didn't mention this explicitly, but when you shift left, of course you have to introduce, if you shift left by 1 bit, you have to introduce a new bit on the right. Which one do you introduce? We introduce 0. I think that's a fairly natural thing. Not to say that it's the only thing, and we will see in a minute, where that's not, right, that exact logic is not always exactly what we do, but in any case. But when left shifting, we introduce a 0, so if you left shift twice, then this introduces 2 extra zeros. You can also shift to the right, and a lot of the, sort of ideas go the same as usual. Now here, we really will want to ask, do we want to prepend zeros or do we want to prepend 1s when we right shift? We typically prepend zeros for and when we prepend zeros, we call that a logical right shift as opposed to an arithmetic right shift where we prepend 1s. But when we do a logical right shift, we are typically using that on unsigned integers. Like if you take, for instance, this example and you right shift it, it occurs to me, I don't know if they make this point, but a left shift is kind of like multiplying by 2. Do they talk about that here? If they don't, it feels like a good thing to point out. Let's take, for instance, let's just take a really easy example and say that, like, if you had 4 bits and you take the number 1 and you bit shift by 1, then it becomes this. Of course, it takes no thinking to realize that it becomes this. But the point is that this was the representation of positive 1. Let's just talk about unsigned integers for now. And this is the representation of the number 2. What if we did it again? What if we take this thing and bit shift by another 1, which, ultimately is like taking this and, bit shifting by 2 by the time we come down to here. But anyway, and then this turns into 0, 1, 0, 0. Well, that's the representation of 4, right? So every time you bit shift to the left for unsigned integers with no overflow, you're effectively multiplying by 2, which is a very valuable thing. We'll see probably many instances where that is so valuable. But so bit shifting left is like multiplying by 2. Bit shifting right is like dividing by 2. Of course, again, right, losing or truncating values makes that you have to have some caveats. So if you had, for instance, 0, 1, 0, 0, and you right shift by 1, then of course this is 0, 0, 1, 0, which is like taking 4 and dividing by 2 and getting 2. So that's what that is. But, like what if you took the representation of 3, right? Basically, the issue is what about an odd integer, which, by the way, is the same thing, right? An odd integer is just the same thing as an integer that ends in the bit 1. So what if you right shift that by 1? Of course, because we, especially with logical right shift, we prepend to 0, and so we get this, right? The rightmost one simply gets truncated, so what this effectively is like, right? If this is the representation of the number 5, and you divide 5 by 2 and you get 2.5, but that's kind of due to like a remainder of the division, which is going to be effectively this bit, and that is simply getting dropped. So effectively what you do is simply truncate the decimal. If you that's just a way to think about it. It kind of corresponds to what's really going on. And so that's why here you get a 2, is that if you think about it, you're kind of taking 5, divide by 2, and then truncate any decimals. So bit shifting to the left and right for unsigned integers is like multiplying and dividing by 2. And we'll see how, as long as we use the arithmetic shift, then the same is true for 2's complement. This takes a copy of the shifted value's most significant digit. So let's see an example. So let's say that we have, and by the way, this will again correspond to division by 2, this time for unsigned integers. So let's pick a number like 1001. And we know that if 1000 is -8, we've seen that a couple of times, then 1001 should be -7. So this is the representation of -7. And let's talk about an arithmetic right shift. And what does this evaluate to? So this evaluates to, we make a copy of the leftmost bit so that 1 is a copy. Then we just take everything else and move it down, so we get 100, and this final bit simply gets truncated off. Now, if we hope that this is somewhat like division by 2. So let's think about taking -7, divide by 2. We know that the result should probably be negative. Now, let's maybe even actually just say that this is -3.5 and take it from there. So if this is truly -3.5, but when taking integers and returning integers, we know that we can't have this decimal. So what we almost always do in a situation like that is we truncate. But so does that turn this into -3? No. What you kind of have to keep in mind, maybe just think of it as a matter of consistency, is that when we divide by 2, we should round down. But is -3 down from -3.5? No, -3 is up from -3.5, right? Because basically for negative numbers, the sort of greater their magnitude, the more leftward they are. So in any case, we do not turn this, right, or when we kind of truncate, we do not round this up to -3, rather we round this down to -4. Now, let's see if our bit shift agrees with that. Is this the, binary 2's complement representation of -4? Well, if there's any challenge in knowing what this number represents, we can always negate. So to negate, we're going to bit flip, add 1, and so we get this. And that is the representation of 4, and it's the negation of this, so this must be -4, exactly as we would maybe like it to be. So there we go. Okay, that is the left shift, logical right shift, and arithmetic right shift.